Hello, everyone. This is Professor Ma, and this is the short introductions on the sections on multivariable functions. We have the following notation. We use R. Capital R stands for real number, and we use square, and now to present two-dimensional space or XY coordinate cube for three dimensional. And in this manner, we can say, oh, and the general mathematical definitions for n-dimensional spaces is just n tuples of numbers representing maybe positions, that whatever you can stretch your imaginations in geometry to be n-dimensional space. Mathematics is that. But a two variable real functions means you take numbers and you assign a two variable in two-dimensional space, then you assign that to be an output. And then, of course, a three variable real functions means you take the R3 into an output. You go to some W and Rn, then a formula, then a real functions from Rn means you take a m variables point into some output. Okay, and in this case, oh, by the way, and in one variables we have f of x equal to some output. Yeah, I use y already, otherwise y, z, and t. Okay, and then this we say, oh, go from real to real, one dimension to one dimension. And this one, of course, we say, oh, f is a function from two dimension to real number. And then we have over here this function. We'll say, oh, f goes from R3 to R, and the output is a real number. And this, of course, we say f goes from Rn to R. And then, of course, you can imagine we can have different functions for R into R square or something like that. But that's for the future. So here is a formula in two variables and z, and we can evaluate and can ask what's the domain, what are the restrictions on x, y, and this one has this one has no restriction. For example, A. Well, however, for example, B, there is a restrictions for g of x, y, and for g of x, y, plugging 0 to, you can see what it plugs in. We get outcome -1. And the domain, in this case, because it's a fraction, so the domain consists of anything as long as the denominator is not 0. And then when denominator equal to 0, you factor, then you find out in those two equations are the points that make the denominator 0. So you have to exclude these two lines. So the domain is everywhere of these two dotted lines. And to see the graph of two-dimension, of two variable functions, we did that before we talked about the level surface. That is, we assign different number to the z, then we see the contour line. And so here are the examples of contour line for a plane. And this is the example of contour line. As z go from center, it goes higher and higher. And so in this contour line where we start from the highest point, z equal to 10, then go lower and lower. So it goes the other way as a tip. Okay. And the corresponding red line. And so on this contour line is on this surface over here, this one over here. The green line, of course, is up there, and the green line is over here, etc., etc. About this one, we had this little review on quadratic surface. If I set different values of z, for positive numbers, z, I will get ellipses. In particular, z equal to 1, I get the cross sections, the control line is ellipse in the x directions 2, in the y directions 3. Okay. And then if I set the denominator to be 4, and that is, if I set this equation to be z4, I divide it by 4 over here, so it's 1, and divide by 4, this becomes 16, this becomes 36. Then this has x square root of 16 square root of 36, 6. And so I got a bigger circle. And if I use 9, okay, and instead of 4, if I use a number 9, z is equal to 9, then I do the same thing. I divide by 9, so this is 1. Then this becomes 36. This becomes 81. Then I'll get even a bigger circle. So I get this elliptical hyperboloid. How about this one? Well, this is the saddle point. So I'm going to go through it. Okay. The saddles. And how about these fractions? This one, if I set z to be a constant, first of all, z has to be positive, right? Because right hand side is always positive. So, and if I flip this over, and then depending on what z is, then I get circle. When z is 1/9, I will get different circles of different radius. And the point it is, the smaller the z, the higher the z, the smaller the circle. Okay, look, when z is 9, the radius of circle is only 1/3. When z is 16, the circle even shrinks smaller. In other words, we're getting a tuning out here. And these are the these are the contour curve, and this is what the three-dimensional the surface looks like. How about these? And well, this is in a similar fashion the way we deal with these problems where we get a bunch of circles. In this one, when we do the algebra, when we get to set z is equal to different constants, we find we are getting equations of hyperbolas. In particular, when z is 1, I get a hyperbolus as over here. When z is equal quarters, actually I get the hyperbolus out here. So this is 0 equal to 1, z equal to 4. Of course, I get both sides. 1/4, sorry, I gotta reverse numbers. When z is equal to 1/4, I get the outside set. And similarly, if I were to set the z to be negative, then the positions of x squared, y squared switch, the sign switch is in terms of y squared minus x squared. And then the corresponding level curves will go in opposite directions. Okay. And in other words, if I were to come in from this side, then the level curves are be climbing higher and higher. This goes up, higher and higher, up. But if I'm coming in from these directions, the z becomes more and more negative when this actually sink, goes lower and lower. And from the other side too, the lower I go into a chasm, go down into a whatever you want to call a valley, into except it has no end. So this is what the surface. And then we have like here's a three-dimensional function from R3 to R. Okay, in corresponding to level curves from R2 from XY to Z, and this is from XYZ to W. And corresponding to the level curves over here we have level surfaces. That is, if I set W to be a constant, I get the equation XYZ, which is a surface. On that surface, XYZ equation equal to a constant. Okay, so for example, let's talk about these equations. Okay, XW equal to 3 variable X squared plus Y squared equal to Z squared. If I say set W to be 1 or 4 or 9, and these are equations of spheres in 3 dimensions, surface of sphere. This is in particular X squared plus Y squared equal to Z squared equal to 9. This is a sphere of radius 3, right? So if I set different W to be positive number, I get different concentric spheres. So on these particular spheres, surface of sphere, W is equal to 1. On this sphere, W equal to 2. On that sphere, W equal to 3. Of radius 1, 2, 3. And what are these surfaces can represent? And they, for instance, they can represent the light intensities. Okay, of same light intensity. For example, if I have a light source over here that's glowing and sending light or energy out uniformly in all directions, and then on this distance, on this sphere, then the light intensity from that distance, we will see exactly the same light intensity from the source. And if I backed out another layers to these layers, then of course I will get another dimmer light intensity. And think about when we're going away from the sun, we're trying to see how intense the light of the sun is. And in particular, according to the law in physics, that is, if I twice as far, then this is going to be 1/4 as thin. Okay, if I measure this is 1, and then the light intensity is 1, then twice as far out is going to be 1/4. And what if I'm 3 times as far? Then outside here on that surface, the observation will be 1/9 of the intensity that's measured at distance 1. So these are, so if you want to call this is equal light perceived surface. Okay, it's a level surface. Okay, or could be heat, on that surface that it had the same temperature. So these are useful for physics. Okay, these are called level surfaces. Now we talk about limits in multivariable functions, and in one variable, a limit exists if the left limits and the right limits is equal to the function value. They all coincide. Okay, the left limit is equal to the right limit, and then the functions actually plug in the hole right there. But in multivariable functions, a little bit complicated because there are more than left and right. If I want to talk about the limit at a point approach AB, there are on the picture there are many ways that I can choose my number x, y to calculate limit. I can choose my x and y to be fixed on some prescribed curve or line. Say, oh, I want my x, y to follow these equations as they get close to the point AB, and I want to know what the limit of that will be. And that causes a little problem. For example, okay, if I want to evaluate the limit of y over x, as we approach 0, 0. Well, now it depends on how we approach 0, 0. If I insist that x and y, that these points that's getting close to 0, 0, I insist that y is always twice of x. Okay? And if that's the case, then what I see, the limit of the function is always equal to 2x divided by 2. It's always 2. But if I were to choose on the curve y equal to 3x, then the limit will be 3x over x as x approaches 0 over 0. Then that will go to 3. And so In order for us to define what limit is, we require the following things. That it doesn't matter which continuous curve you go through AB, the limit of x, y approach on that curve is equal to every other curves. Approach from every other continuous curve equal to some number limit L. Okay, then we say the limit exists. And of course we say, yeah, then we say it was continuous. There's no hole there if the f of x, y actually equal to L. Okay, the limit exists if all the limits coming from all different whatever curves you can think of. The limit calculation all turns out to be the same numbers. Then the unsurprising things is say for every elementary functions, and if the points inside the domain, that means it's a neighborhood that sits inside the neighborhood sits in the domain. If that's the case, then the limit is exactly what you expect. It's just you're just plugging the numbers. Okay, and this is basically all we're going to say about the limit. And for instance, when x, y approach 0, 0, because x plus y squared goes to 0, so limit of that is 1. Okay. And this we can simplify first, and then that limit is going to be 0. And so these are the basic facts about limits in multi-dimensional, multivariable functions. Okay, that's it. Have a good night. Okay, and see you next time. Bye-bye.